So here we're taking a look at section 6.2, working with multiplication properties of exponents. Now we are working with this section and exponents as a generality. The overarching, most important thing that you can do in all of these problems that you're working with exponents with is correctly identifying the base of the exponent. If you cannot do this correctly, the entire problem falls apart and everything else around it does also. So our main definition of an exponent we have here is something to the effect of x to the a power, where x is the base, should just be the base, not based. So x is the base, and a is the exponent. And exponents denote repeated multiplication of the base, meaning, as an example, if I had 2 to the third power, that would mean 2 times 2 times 2 if we expanded that out. So it's the base multiplied by itself a many times, whatever that exponent is raised to. We'll go through a couple examples of what that looks like if we expand these things out down below here as well. But again, that's our main definitions that we have with working with exponents. And again, with all of these, I cannot emphasize the importance and how crucial it is to correctly identify the base for every exponent you are working with. Lots of people just run through it and errors show up. The entire problem will fall apart if we do that. So the main properties that we have here, the three that we're going to be going through with this, are the product rule, power rule, and product to a power rule. So the product rule states, as in general terms, if I have a to the m times a to the n power, then my result is going to be that same base of a, but the exponent is going to be m plus n, meaning the exponents are going to add together. So our main way of thinking this, if the bases are the same and multiplying, then the exponents add. This is another part, correctly identifying the base of the exponent. If I have two random things multiplying together with exponents attached to them, I can only apply the product rule if the bases are the same. If the bases are different, then I don't really have any ability to add those exponents together. I cannot do anything with that. Our next one that we have is the power rule, which states that if I have a to the m all raised to the n power, my result is going to be a to the m times n power. And we're assuming in these instances that a, m, and n, and b are all just number values. Well, they could be variables, but our exponents are generally denoted with number values. So our power rule, as a generality, states that if an exponent, we have here a to the m, is raised to a power n, the exponents multiply. So our result will just be m times n. It's going to be a to that m times n power. We can also see this, and we'll go through an example or two of this, of if we were to expand our original statement and actually write it out as a to the m times a to the m times a to the m and so on, we'll see that we'll get this exact same result. And I'll go through a couple examples, one or two with that down below here. And our last rule that we have is the product to a power rule. So here we have the product a times b to the m power. The result is going to be a to the m times b to the m. So if as a generality, if a product is raised to a power, then the exponents multiply. So I have a essentially to the first power, that invisible 1, b to the first power, that invisible 1, and what's happening to the exponents there? Well, that a to the first times m gives me m. That b to the first raised to the m power also gives me b to the m. We get our examples there. So the main reason we have these properties over anything else is we can basically use these rules as shortcuts to find our answer instead of expanding and simplifying the bases over and over and over again. And we'll see a couple examples of this. I don't think we're going to be able to get through all of these, but the main rules of them are going to apply all the same. We can use these as shortcuts to help us get through and solve these things a bit more quickly. So I'm going to jump on over to our Blackboard, and we're going to go and reference these examples. Looking at our time, we are probably not going to be able to get to all of them, but I'm going to kind of jump around between these. I think it's going to be really good to see each of these rules applied. So we'll jump us over there. So the first rule that I want to go to or compare with these is our first two examples that we have, and I'll throw in it did not make its way into these notes explicitly, but I want to go into emphasizing that we need to correctly identify the base of an exponent. So what that looks like, and I'll write this out here, 6 to the second power versus negative 6 to the second power versus parentheses, the quantity negative 6, I'll raise the second power. So again, with all exponents, whether it's numbers, whether it's fractions, whether it's variables, anything with it may be, correctly identifying the base is absolutely crucial to solving these things. There we go. So in our first example we've been given, this 6x squared, the base is that number 6. In our middle example, we have negative 6 squared. I think it's the middle and the right example where we get a lot of hang-ups on this. So I'm going to let you guys think on it for yourself. You don't need to type anything in and respond to it, but think on it for yourself here for a quick second. What is the base of our middle term, or middle example, that negative 6 squared? And what is the base of the problem on the right, the quantity negative 6 to the second power? What is the base of the middle one? What is the base of the last one? Again, I'll let you guys think on that here for a quick second. So looking at our middle problem that we have, this negative 6 to the second power, the base of that exponent is just going to be the number 6. It is not going to include the negative sign. If we look at the last example, the quantity negative 6 to the second power, the base of that is going to be that negative 6. And the reason behind this, if we're looking at, where's my spotlight? There we go. If we're looking at comparing these two examples, the last example has what's raised to the second power? Well, we have this parenthesis inside here, and that says everything that is inside this set of parentheses is going to be raised to the second power. This is the parenthesis to the second power. So if this is a positive, if it's a negative, if it's a fraction, if it's a decimal, whatever, anything inside of the parentheses is going to be the base. So that's where we have a base of negative 6 here. Now in our middle example, the thing directly to the left of the exponent is just the number 6, not its sign. So in this instance that we have here, the base of the exponent is just the number 6. The negative out front is just along for the ride. There's a huge difference between I'm including the negative here because it's encompassed within parentheses, and I am not including the negative because it is not included inside any set of parentheses. So this is a very, very big distinction that needs to be made as you are going through and identifying the base of these exponents. I think the whole number, the positive numbers, is really nice and pretty straightforward, but as soon as negatives come into play, having parentheses or not having parentheses is absolutely vital to how we go through and we calculate this. So if we've correctly identified the base of our exponent, then everything else in the problem is going to stay the same, and we can expand and then multiply things together if need be. So for our first example, if the base is 6, if I were to expand this out before I multiply it, it's the same as saying 6 times 6, which gives me 36. For my middle example, that negative out front, it is not part of the exponent, so it is just along for the ride. The base is 6. It's raised to the second power, which means I'm going to have a negative 6 times 6. And 6 times 6 is 36. Again, the negative out front is just along for the ride. And in our last example, the base is the quantity negative 6. So expanding that out, that would be the instance of negative 6 times negative 6. And a negative times a negative is a positive. We get our answer of positive 36 there. So correctly identifying the base, especially when we have positives and negatives showing up, primarily with negatives, is absolutely critical with this. If we do not correctly identify that base, and again, parentheses is the huge giveaway on whether we're including that negative or not. If there aren't parentheses in there, that generally means we are not going to include that negative for our final answer, or as our, I shouldn't say as our final answer. We will not include that as the base of the exponent. Okay, so I'm going to start taking a look at some of the other examples from that same portion of the notes that we had. I'm going to move us over here. We'll start going through some of these other ones. So I'm going to take a look at, we'll take a look at number 3. So number 3, we have 3 to the 3 over 5 raised to the third power. Now again, we need to correctly identify the base of this exponent. The thing directly to the left of the exponent is a parenthesis, which means everything inside the parentheses is being raised to the third power. So you could write this thing out with a fraction at least. You could write this out as 3 to the third power over 5 to the third power. Use your calculator if you need to and determine what are each of those numbers. Well, that's going to be 27 over 125. Now, alternatively, if you wanted to write this out in expanded form, you could write it out as, again, the base is 3 over 5. So you could do 3 over 5 times 3 over 5 times 3 over 5. Again, the exponent says we're going to have the base multiplied by itself that many times. 3 times 3 times 3 is the same as saying 3 cubed. 5 times 5 times 5, it's the same as saying 5 cubed. And then we get the same answer. So 2 methods, 2 ways of writing these things out to get to our same answer that we get at the very end. I'm going to jump us here to, let's take a look at this. Let's go with, we'll take a look at example 5. Okay, I'm trying to keep track of our time, so we might not be able to get through everything, but at least be able to see some of these. So example 5 is giving us a squared b cubed times a to the 10th bc cubed. So I have everything multiplying together here. All terms are multiplying, or all variables are multiplying here. So if we wanted to write this out for ourselves, okay, well, one of the nice properties that we have with multiplication is if everything is multiplying together, I can reorder how that multiplication is happening and keep the same value. The idea behind it being, okay, if I have 2 times 3, it's going to give me 6. It's the exact same thing as if I reverse those numbers and did 3 times 2. It's also going to give me 6. So if we were to write this without any parentheses in here, it would look like this. We'd have a squared, b cubed, a to the 10th, b, c cubed. Written out like that. If you wanted to put these little dots in here separating each of these out or denoting multiplication, you're welcome to do that also. It's not required, but it's an option. And if you wanted to start grouping these variables together to see these properties in action a bit more, let's do that. So we have a squared times a to the 10th times b cubed times b times c cubed. So this is very similar to what we did with the addition subtraction portion with these things, where we're just reorganizing it so I can see here's my a's multiplying together up here. Here's my b's multiplying together. Oops. B's multiplying together, like we had from up here. And the c, well, there's nothing else I can multiply with it, so it's just along for the right at the very end. Now, looking at a squared times a to the 10th, the product rule states that if the bases are the same and multiplying, then the exponents will add together. So a squared times a to the 10th, the a is going to stay the same, base remains, and the exponents add together. 2 plus 10 is going to give me 12. Looking at b cubed times b, the bases are the same, they're both b's, which means the exponents will add together. B cubed times b, there's nothing written there, it is implied that there is an invisible 1 that's hanging out there. So b cubed times b to the invisible first, it's the same as saying b to the 4th power. Ugh, better 4. There we go. Well, better 4. And then that c cubed at the very end, nothing is happening with that. There's no other c's in here, so I can just leave it as c cubed. Nothing else. Can't do anything else with this problem, so I'm good to go there. There it goes, boxing this thing. Okay. We'll take a look at, let's look at example 6. I think this is a really good example of expanding versus our properties. So example 6, we're given t squared to the 5th power. So correctly identifying our base, everything inside the parentheses is being raised to the 5th power. So we have our power rule that states if an exponent is raised to a power, the exponents will multiply together. So I have t squared raised to the 5th power. So it's an exponent raised to a power, which means that my solution is going to be t to the 2nd times 5th power. 2 times 5 is going to give me 10, which means I'm going to get t to the 10th as my final answer. Now, alternatively, again, you don't need to do this. This is actually the reason why we want to memorize these rules, so we don't have to do this. So alternatively, if we correctly identify the base, this quantity t squared, I can expand this thing. This is kind of our nuclear option if we don't know what to do. We can expand this thing by writing that base multiplied by itself however many times based on our exponent. So t squared times itself 5 times. And now we could use the product rule to do this. So our first two, or everything here has the same base. It's all multiplying. So all of the exponents are going to add together. So 2 plus 2 plus 2 plus 2 plus 2. The same as saying t to the 10th power. We have the same answer. So again, both options are available to you. I would highly recommend you get comfortable with using the properties though, because it's going to save you from having to write out a bunch of things, especially when you start getting to larger powers or larger exponents showing up, and that becomes very not fun to work with. Okay, so we're going to jump to, we'll go with number 7 here. Just going to move us over. So number 7. So we're given the quantity negative 3b to the 7th, all raised to the 3rd power. And again, we need to correctly identify the base of the exponents. So we have two exponents here. The base of the exponent of 7 is b. The base of this 3, an exponent, is everything inside the parentheses. That does include the negative out front of the 3 for that coefficient. So in this instance, you have a couple ways you can write this out for yourselves. One of the ones that I really like is don't know if everyone has me on the webcam or whatnot, but I'm doing air quotes here. You're going to, quote, divide each of these parts of the base and then raise each of them respectively to the 3rd power. And I put a lot of air quotes around divide, and you could probably think of it as, quote unquote, separating these things out and then raising each part to the 3rd power. So what that looks like is I have negative 3, the quantity negative 3 to the 3rd power, and the quantity b to the 7th raised to the 3rd power. And now I work with it in individual parts. Just work with the number, just work with the variable ones. So negative 3 to the 3rd power, well, it's negative 3 times negative 3 times negative 3. So negative 3 times negative 3 is going to give me a positive 9. Positive 9 times negative 3 is going to give me negative 27. And then b to the 7th, all raised to the 3rd power, again, using that power rule. The exponents are going to multiply together. 7 times 3 is going to give me 21. So I have negative 27 b to the 21st power. And I'm done. Now again, if you want to go with the alternate version, which is you expand and simplify, you could write this out, correctly identifying the base. Whoops. Just like this. So you have it negative 3 times negative 3 times negative 3. It's going to be that negative 27. B to the 7th times B to the 7th times B to the 7th, B to the 21st. And again, gets you the exact same answer. So one of these uses our properties. The alternative method is expanding and then simplifying. You're welcome to use either one that you would like to on the homework. You're welcome to use either one you would like to on the test. I think to me, I would recommend getting used to the properties. They can save you some time, especially, again, we have large numbers showing up with these. Okay, looking at our time here, I'm going to try and get through, we'll take a look at number 9. So for number 9, we've been given 2/5 a to the 4th b to the 3rd times 15a b to the 3rd. So here I have numbers, I have variables showing up, but everything is multiplying together, which is great because we can use our properties. Now, when you get instances like this, and just pretty much with all of these, if we are told to simplify, we're going to follow in PEMDAS as we need to, so remember that. More specifically, though, with problems like this, I've got numbers, I have A's, and I have B's. Work through these piece by piece. My recommendation, work with just the numbers, work with just the A's, and then work with just the B's. If that means you have to write it out for yourself like that, great, do it. What that could look like for this one, because again, everything is multiplying together, you could write this out for yourself as 2/5 times 15 times a to the 4th times a times b cubed, times b cubed. So again, numbers, A's, and then B's. And again, in the second line of work, you can write it out for yourself like that. If you can do a lot of the stuff in your head mentally, great, good for you. I can't all the time, so I need to write it out. And then now work with it, just the numbers, just the A's, just the B's. Split this thing up and do it in parts. So 2/5 times 15. That 15 is implied to be over 1. The 5 cancels, the 15 becomes a 3. That's going to give me 2 times 3 is going to be 6, so I get 6 are my numbers, my coefficients. A to the 4th times a, again, it's implied to have that invisible 1 in there. So a to the 4th times a to the 1st, the bases are the same, and they are multiplying, which means the exponents will add together. It's going to give me a to the 5th power. I have b cubed times b cubed at the very end. The bases are the same, and they are multiplying, which means I can add the exponents together, which is going to give me b to the 6th power. I can't do anything else from here because the bases are all the same and we have coefficients, and that's fine. We have our final answer here of 6a to the 5th, b to the 6th. And looking at our time, we're not going to have time to go through other examples with these. But again, there's a whole bunch of them that are available in there. There are more examples in the textbook itself, so I would recommend taking a look at that if you would like more. And then the other one is the overarching part with a lot of these problems. I'll jump us back to our notes to show this. If you are unsure where to start with any of these problems, most of these are going to say simplify or evaluate the following, or the given expression or something like that. Remember that when we see the buzzword of simplify or the buzzword of evaluate, that should be the flags going off in our head of we are going to be using PEMDAS, our order of operations, if we do not know what to do first. Actually, just as a generality, PEMDAS is governing what we do. So make sure you are following PEMDAS, that order of operations, with all of these problems. Make sure you're doing all of them correctly. Okay. So that is everything for our 6.2 material with multiplication properties of exponents.